Hello, grade 11s. We are going to talk about an introduction to rates. Now, when we talk about rates, we have to probably describe what the heck a rate is. Now, a rate is something that is used to describe how one quantity changes in relation to another. So when we take a look at this, we have two quantities that are changing, and we're looking at how those change at the same time or respective to each other. So a rate, because it has two quantities, will have two separate units. So two quantities that will be measured in often different units. Now, here are some examples of rates. So 60 kilometers per hour. So it measures two things. Now the rate we often talk about is driving speed. So how fast something's going. Oops. You see that on speed signs. You see that on, I don't know if you're watching F1 and you want to know how fast the vehicle is driving. That's typically what kilometers per hour talks about. Now, what are the two quantities? Well, the first one we had was in kilometers. What's measured in kilometers in this case? Distance. The second quantity is measured in hours. What's measured in hours? Time. So my distance versus my time is what gives me my driving speed. And we could do this for every single one of these here. So my next one is $2 per apple. What does that measure? It measures my price. And again, I can look at my units independently. My first unit is in dollars. What's measured in dollars? In this case, cost. My second unit is apples. What's measured in apples? Well, the amount of apples would be measured in apples. If you ever get a weird unit like apples or lobsters or thumbtacks or sticky notes, what it's measuring is typically the number of apples or thumbtacks or sticky notes or whatever else I said earlier. But it's typically that value. So if you're like, whoa, what's measured in apples? Number of apples. What's measured in, I don't know, collectible dolls? Well, collectible dolls. The number of collectible dolls are measured in that. Okay, so something to keep in mind. Moving on. So I could do 100 megabytes per second. You might have seen that before when talking about internet speed. What's measured in megabytes, might you ask? Solid question, team. Well, megabytes measures storage capacity. So how much capacity your computer or device can store. And then what's measured in seconds? Well, of course, that's time. So when we talk about internet speed, it talks about the megabytes, the amount that you can access over time. And the more you can access in a short period of time, the faster your internet speed. Okay, I'm not going to go through and highlight the rest, but things like beats per minute, that's your heart rate. And we're taking a look at the number of beats in over time. Grams per liter, that measures density. If you think back to grade 8 science, what a time. But again, it's the mass in grams over the volume measured in liters. And last one, 10 liters per 100 kilometers. That's actually measuring something called fuel efficiency. So if you look at purchasing a car one day, they will often tell you the fuel efficiency of that vehicle, assuming that you're not buying electric. And that is measuring the change in the volume of liters of fuel over or compared to the distance in kilometers that you were driving. Now, these are all great. We can see that every single rate has two units. Common things to kind of point out here are rates are really just examples of slopes. I don't know if you remember much about grade 9, but we talked about rate of change. And then suddenly in grade 10, we talked about slope. these are identical things. Both of them refer to the change in my dependent variable divided by my change in my independent variable. Now, we are going back and referring to them as rate of change or just a rate at this point. But this is what I've got. And my rate can really clearly tell me what unit is belonging to which variable. So my first unit is going to be my dependent variable, which is this one. My second unit, hours, apples, seconds, minutes, liters, kilometers, will refer to my independent variable. So if you ever have difficulty identifying independent and dependent, we can always also look at the rate to give us a good indicator of which variable would be which. Okay, now you might be thinking to yourself, why does this matter? Like, truly, why does this matter? Mostly for comparative purposes. So if I want to compare various options, maybe you go to, I don't know, Sobeys or Superstore to buy your produce, and one is measured in, like, apples. The cost of apples is $2 for every kilogram, and something else is $1, I don't know, $1 for every pound. And you're like, okay, if I had rates with the same units, I could compare them really, really easily. Or if I had $2 per kilogram in one and I had $1.98 per kilogram in the other, side by side, super easy comparison. So comparative purposes are important. Rates can also help us predict outcomes. So if I'm driving at a speed of 100 kilometers an hour and I have to go 800 kilometers to reach my destination, I'm going to predict it's going to take me 8 hours, right? So I can use that for prediction purposes. And then it also helps us understand graphs, understand trends, make decisions, etc. So we are going to start by talking about graphs and rates and how they're connected. And we kind of already very simply sidebarred and talked about it already. The rate, also referred to as rate of change, is the equivalent to the slope. Now in grade 10, the reason why you focus on the word slope is because you're mostly focusing on the graph. You're not really focused as much on the context or what's happening there. You're focusing on the graph and building the equation with the numbers provided, and not so much in terms of interpreting what's going on. In grade 9, we barely use the word slope. We use rate of change a lot because we're focusing mostly on the context. We're not really dealing with any really challenging numbers. We really want to make sure that that understanding is linked to the context in the scenario, and then the numbers are secondary. So we've actually technically know how these two things are related. Let's just kind of put this together. So graphs, obviously they're visual tools. We know on a graph we have an x-axis and we have a y-axis. The x-axis is on the horizontal, the y is on the vertical. Now, when we take a look at which is which, the independent will be the x, the dependent will be the y. So when we were just talking about this graph over here, this change would go here, and this change would be graphed there. Our variables, based on our rate, go in very specific locations. It is not a free-for-all. It is not a mix and match. Okay. The rate between two variables will be represented by the slope of the graph. When we graph things, we are most commonly used to graphs being straight lines when we're talking about slope. So if I have a graph that is represented as a straight line, that means my rate is constant. Because my slope is constant, right? If I had a perfectly straight line here, and I took a look at a bunch of points along that graph, the amount that I'm increasing and the amount that I'm traveling sideways would be consistent and constant the whole time. So I'm consistently going up, but it is going up by a constant amount, a non-changing amount. However, what we're less used to is a graph that makes a curve, or truly if it's made up of a connection of a bunch of various lines. This means that the rate is not constant. Or you could say that the rate is changing. So if I'm taking a look at slope, remember, slope represents the steepness of my graph. So my slope here, and my slope here, and my slope here are all different. Right? This slope is much more gentle than this slope. And if you were sitting at the top and for some reason traveling towards the left instead of the right, like a fool, you would notice that the beginning of this slide would be much more steep and the end of this slide would be much more shallow of a slope. Go much faster at the beginning and then much slower at the end. That's because your slide is not one constant slope. It is a changing slope. That's what a curve shows. Okay, moving on. How to find a rate from a graph? Well, we can do a bunch of different things. And we've actually talked about all of this last year as well, so none of this should be really new. I'm just going to forcibly use the word rate because that's what we're focusing on. Last year, you would have used slope way more often. So you might have referred to slope, well, you definitely referred to slope, as the change in y divided by the change in x, or the change in the dependent variable. I'm going to write that there, dependent, over the change in the independent variable. And you might have represented it as change in, or you might have shown this triangle shape next to the y, and that triangle is just a shorthand for a change in. Okay? Now, how are changes measured? Well, quite simply, they're measured by your final value minus your initial value. So this is my last y value that I'm interested in, subtracting the first y value that I'm interested in. And then divided by the second x value that I'm interested in, minus the first x value that I'm interested in. The other way that you might have talked about it last year is rise over run. Now, all of these are accurate, and all of these make sense, and all of them can be used. However, there are some that are like better suited for graphing purposes and some that are better used for non-graphing purposes. So all of these can be used for a graph, but this one particularly, which is just a reflection of this guy here, but the ones that I've highlighted in green, you can also use without a visual graph representation present. As long as I have two sets of values, one set of 2 points for my y, my dependent variable, and one set of 2 points for my x, my independent variable, I can plug those in, never have a graph in front of me, and still calculate that rate. I don't need a graph to be able to see what a rate is going to be. I can still calculate that slope without it. And in grade 10, you would have actually done a decent amount of work of calculating slope before graphing it. You might have been given two values or two separate points along the way and then had to find the slope and then graphed it after. So that is still holds true here. If I don't have a graph provided, but I have two sets of points, two y values and two x values, I could use these green highlighted options to help me calculate that rate. Okay, Rates. Again, grade 11, we are focusing on the context again because we are applied math. Everything has to be application based. So the units are really, really important. Last year, your slope, you just told me it was 7 or negative 2/5. But this year, the units for that slope will matter. The units for that rate will matter. And if you noticed, again, backtracking over here, we always had two units, something per something else. And it could be written as something per something else, or it could be written with a slash in between. That is okay because that slash means division, and one of the words for division is per. So either or is all good here. But when we're calculating the slope, we need to make sure units are there. Now, the units are pretty simple. The units for my dependent or my y go at the top in the numerator. So the units for the numerator will match the units for my y variable. And in brackets, I'm going to write dep for dependent. And then similarly, units for, what color haven't I used? My denominator will be units for my x, or my independent variable. Okay, we are going to jump into some examples. The first example is a graph. Our goal is to find the rate. We are going to call it rate. We are not going to call it the slope. But our rates all need to have units associated with it. Now again, our rates can be found by acknowledging what the slope is because they will be the same. How might we do that? We might look for the change in our y or the rise and then compare it to the change in the run or my x. I just then need to make sure that units are available there. So my rate. I am going to find this graph here, and I'm looking at my y value. Oops, that's not a highlighter. And my y value is measured in dollars. So when I'm looking at a change in my y value, I'm going to get a dollar amount of change. Now I'm going to look for 2 points that are easy to read, which I'm going to go for these two. And I'm going to see how I change. So I've started at $8. I'm going to $14. So I went up $6. So my rise is positive $6. Now, my run started at 1 and ended at 3. And what are the units there? The units are in hours. So I went up, not 1 hour, 2 hours. So I have $6 for 2 hours. Now, of course, when we have the opportunity to, we are going to simplify. 6 divided by 2 is simply 3. So I have $3 per hour. Something that's really important is that even though you're like, hey, look, this 2 goes away, technically becomes a 1. Now, am I going to write that 1? No. However, I am going to make sure that if hours were in the denominator before, hours remain in the numerator now. Last but not least, this is my final answer. I'm great. I'm happy. But last but not least, in terms of rates are often written as fractions horizontally, right? Like if you go and drive around the city and you're like, this is 50 kilometers per hour, it's typically written horizontally. It's typically not written like this. I think people get freaked out about fractions, but there's fractions everywhere, so chill. So if you'd like to, you can write it horizontally as well, because it means the same thing. It's still a fraction. It's just a fraction written in the alternate, direction. Okay. Next, we have Carter and Carly. They love to bike, and they're taking part in a crazy long bike tour. After 2 hours, they've biked a total of 95 kilometers. After 4 hours, they've biked a total of 190 kilometers. Okay, this is not a graph. Now, a graph, like we've done above, easy to read for identifying the slope. You've practiced identifying the slope forever. However, this does not have a visual slope there. So I am going to use kind of these middle two strategies here to figure out my life. Now, when I figure out my life, I do need to know which variable is which, right? I do have two values for time, and I do have two values for distance, which is great, which means once I have them, I'm going to plug them into this, and life is going to be good. But I need to make sure I'm plugging the right numbers into the right part of the fraction. I can't just randomly put kilometers at the top and hours at the bottom, or hours at the top and kilometers at the bottom, because I'll get very different rates and one of them will be wrong. So I do want to just quickly identify what my variables are. One of my variables will be independent, the other variable will be dependent. And if I'm taking a look at the units, so I've got hours, I've got kilometers and kilometers, it should tell you what those variables are going to be. Right? One's measured in hours, which has got to be time. And the other one's measured in kilometers, and that's got to be distance. Now, when we take a look at independent and dependent, pretty much 95% of the time is going to be the independent variable. So I'm going to go and put time there, and I'm going to measure time in hours. And my dependent will be distance in kilometers. Now, do you need to write this out explicitly? No, because my job here is to figure out the rate. However, if you mix these up and we don't take the time to process which variable is which, you can't get the mark for the rate because it's part of the whole question. It's part of that interpretation. So when I take a look at my rate, it's my change in my dependent, which is going to be this guy, divided by the change in my independent, oops, that's not a highlighter, the change in my independent, which has got to be that guy. And again, we are looking for the change in these values, and we're looking for the final minus initial. So here's one sentence, I'll deem that as my final. Here's the other sentence, I'll deem this as my initial values. I'm going to plug them in. So my final time is 4, and my initial time is 2. And again, I'm going to keep the units there just because I need them in my... Oh, Miss T, you rookie. I highlighted things in the wrong color, and that could be really heckin' confusing. I put them in the right spot, but I highlighted the wrong color here. So let's backtrack just 1 minute and put independent for my time. And I know that will go in my denominator of my rate. And my dependent, my kilometers, which will go in the numerator of my rate. All is well with the world. I hope you all panicked and went, oh my gosh, my teacher's crazy, and then realized she just made a mistake. Okay, back to this. I'm going to stick with the time. I'm going to stick with it in the denominator first, though. So 4 minus 2 hours. And then 190 minus 95 kilometers. Please keep in mind that it's possible to have negative rates, so please don't just assume that it's always the bigger number minus the smaller number. It is sometimes the other way around. We are just making sure that if we have things connected, like these two values were connected in a statement, so those two values should have the same position. And these two values were connected in a statement, so those two values should also maintain that same position. Okay, we're going to do this math. 95 taken away from 190 is still 95. Yes. 2 taken away from 4 is still 2. And I'm, of course, maintaining my units. I can reduce this, and so can you. And yes, it'll be a decimal, but who says we don't like decimals? That's 47.5 kilometers per hour. And that is the rate in which Carter and Carly are biking. Which I don't know if you know much about biking, but that's pretty heckin' fast. So good for them. Okay. We've got a couple of more. We've got another graph followed by another word kind of, I don't know, description here. Please pause the video and attempt the next two on your own. So fully paused, full attempts. Go. Okay. We are back. Hopefully you've paused. Hopefully you've attempted. So I know my dependent is on my y-axis. My independent is on my x. When I take a look at my rate, I can think about it however I wish. But I'm trying to find some points that line up nicely. I like this one. I like this one. I tend to find the 2 points that line up nicely that are closest together because it'll require the least amount of reduction at the end. However, you guys have calculators. It doesn't matter if you pick 2 points that are really far away because your calculator will do all of that math work for you. When I take a look at this, I'm noticing that I am traveling down and I'm traveling in the dollars region here. So I'm traveling down. How far am I traveling down? I'm going down by $3,000. So I'm putting a negative, and I have $3,000. And then I'm traveling from the right. What are my units? My units are in years. And I'm going and traveling in a positive direction. I'm going up 2 years. When I'm plugging in my rate, yes, I do get negative $3,000 for every 2 years. And that can be reduced to give me negative $1,500 per year. Now, if we think about it, and you're like, whoa, negative money? What the heck? Well, think about the context. It's the value of your car over time. When you buy a car, the value of it, other than like old vintage models, which is a different story here, but if you went to a car dealership and you bought like the brand new 2027 model of whatever it is, the moment you drive it off the lot, your car tends to start to depreciate. Unless you're some rich celebrity who like people want what you touch, or there's some weird, obscure, atypical situation going on. But typically your value of your car decreases, right? The older the model is, the more wear and tear on the vehicle, the lower its overall value. So it does make sense that my rate is negative because the value of my vehicle would be decreasing each year. Okay. Now we got Mia and Harsimran, and they're filling gift bags for the school gift bags from the Heart fundraiser. After 20 minutes, 48 bags were completed. After 50 minutes, 120 bags were ready. Okay, so I've got two different things. I've got something measured in minutes, and I've got something measured in bags. And we can identify those two variables just to make sure we're on the same page here. My independent will be time in minutes. My dependent will be the number of bags measured in bags. Okay. When I take a look, I need to make sure that this set of values is maintained position and this set of values has maintained position. Whatever position I tend to choose, I should get the same final answer. But I have this. So my number of bags will go at the top. I am going to go my final number minus my initial number. And I'm going to put bags there. And then accordingly, I'm going to put my final time minus my initial time. And I'm going to maintain minutes there. I do that math and I get 72 bags in 30 minutes, which is ideal, but can be reduced. And if I plug that into my calculator, I get 2.4 bags per minute. or every minute they are able to complete 2.4 bags for gift bags in the heart. Okay. Hopefully that went pretty well. We have an example left, example that has 2 parts. And based on what you're probably imagining, based on what we see here, we are now going to graph some rates. So, first of all, we need to talk about how to identify a rate. Now, a rate, if you remember from grade 9, and if you remember from the beginning of the lesson here, it compares 2 quantities. So, I'm going to write that, compares 2 quantities, which means it will have 2 units. Things that we can identify, phrases we can identify to indicate a rate is something per something else. Very, very common. Or something slash something else. Very, very common. Other ways to phrase that is my units for every. So like it goes up $5 for every additional person. Okay. Or the words for each. This is not an all-inclusive list, but these are common phrases that you can identify from a word problem to ensure you can appropriately identify the rate. So when I take a look at this question here, I've got Shirley. Shirley has $400 in her bank account. She withdraws $40 each week to cover her expenses. Okay. Now there are 2 numbers in here. Only one of them is a rate. And if we think about the $400, there's only one set of units there. It's just the dollars. So that $400 is probably telling me a starting point here. It is not telling me a rate. However, she withdraws $40 each week. That each. And the fact that there's 2 sets of units surrounding it indicates that that $40 is a rate. That is going to be my slope or my rate of change in my graph here. Now, if we think back from last unit, we know how to graph. We need to make sure we have a title. We need to make sure we have labeled axes, all of these great things. Also a reminder for my rate of change, if I was not able to adequately identify independent and dependent variables before, I should be able to, based on the order of the rate here. Because those words are linked together with that key phrase, either per, slash, or every for each, or just every or each, you don't need the for in there necessarily. Because it's all linked together in one concise way, and a rate will show me my change in my y, or my change in my dependent, over the change in my x, which is the change in my independent. I could identify which variable is which based on the units and the order of my rate expressed to me. Now, I can't just say my dependent is dollars and my independent is weeks. I do have to do a little bit more thought. Those are just the units in which they're measured in. But it can help you kind of start off with that hint. So I am going to graph some stuff, and I'm going to say that my independent is time, which is measured in weeks. And then what's measured in dollars here? It's the amount of money in her bank account. Amount of money in her bank account. I think sometimes people see $sign and they're like, it's got to be cost. This has nothing to do with cost. She's not purchasing something. This is just about how much she has remaining. So it's important that we actually consider the context and go from there. And as for a title, I'll probably say the value of Shirley's bank account over time. So I'm going to go ahead and do that. Value of Shirley's bank account over time. Okay, we want to graph the stuff. Now, I know that Shirley has $400 in her bank account. When? Right now. So, a time of 0 weeks before she even starts withdrawing money, she's got $400. And then I know that every single week it goes down by $40 because she's withdrawing that money. She's not adding to her account, she's withdrawing it. Which means after that 400, that 0th week at the very beginning, the money is going down. So I'm going to see if I can create a scale on my y-axis that goes up to at least 400, but also tries to space things out. When I'm also choosing my scale, I know I'm going down by $40 each week, so it wouldn't make sense for me to jump up by 25s here because that would be really hard to graph. So if I could go up by 10s, sure, but it doesn't look like I'm going to have room. So going up by 20s makes sense, or going up by 40s, but again, I want to make sure to use up as much space as possible. So I'm going to see what that looks like. I'm going to try going up by 20s. And when I say try, I'm like pre-counting. So 20, 40, 60, 80, 1. So I'm going to just see like every 5 would be 100. Will I be able to fit that? Yeah, I could get up to 400. And once I'm happy and know that I can fit that within the space provided to me, I'm going to go ahead and label those. Now, you are more than welcome to label every single one. But keep in mind that I'm able to zoom in on my graph. You wouldn't be able to zoom in on a paper on a test. So if it's hard for you to label every single one, you don't have to label every single one as long as we are consistent with our scale. As for time, it doesn't tell us how long she's withdrawing money for. So I'm going to show the first, few weeks. I'm going to show maybe 5, maybe 6 weeks. We'll see what my graph goes up to. I'm going to make some sizable jumps here. If it told me to show how many weeks she would have until she ran out of money, I would make sure that I can show far enough along the graph. But it doesn't tell me what I need to show as a minimum. And I'm just going to space things out accordingly. Okay. Now I'm going to plot some points. So that $400, as we talked about, must be that initial value. So right now, before we're making any withdrawals, she's got $400. And then after 1 week, she went down $40. And then she went down $40. And she went down $40, etc., etc., etc. So I'm using that rate of change of withdrawing, which implies that negative $40. So I'm going down $40 for every 1 week. Okay. Once I've plotted those points, I can connect the dots here. Now, when I connect the dots, I want to use a ruler. If you do not have a ruler, please borrow a ruler. And when I'm connecting those dots on the right-hand side, because there's still withdrawals that could happen after 6 weeks, she's not out of money yet, I am going to draw an arrow to imply that my trend would continue after what I have drawn. But I am not going to put an arrow on this side. And the reason being is because it doesn't indicate to me that she has more money or had more money in the account and she was withdrawing before this. So I'm just going to leave it as an endpoint. Okay, please make sure that you, just like our linear inequalities unit, our line is legitimately going through our points and we're not just like making the dots really big to make it look good, because trust me, it won't. But also it allows us to make predictions down the road. Like I can figure out a trend, I can figure out where we're going by continuing the graph and seeing new points. Okay, we have one more. We have the temperature of water in a kettle starts off at 20 degrees Celsius at 0 seconds. The temperature of the water in the kettle rises 4 degrees Celsius for every 30 seconds it's been heated. So I'm going to get you to graph this on your own in just a moment, but I do want to point out a couple of things. So sometimes people look at these two sets of numbers and units and go, hold up, I have two rates. How is that possible? And it's not. We do not have two rates here. We have one scenario. We have one thing going on. And we're looking at kind of some keywords here. This is just telling me what I'm at 0 seconds. It's telling me that y-intercept in theory, or my initial value or my starting point. Because at doesn't imply a relationship between the two values. It just tells me a point on my graph. However, the second one has that keyword for every. It implies that it's a repetitive change. It's 4 degrees Celsius every 30 seconds it's been heated. And it's rising, so I know that 4 is a positive, even though it hasn't explicitly stated. I do want to make sure that I'm reading the words because sometimes negatives and positives are implied but not explicitly stated. Can you pause the video? Can you please graph? And then we'll compare. Awesome. Go. Okay. I'm taking a look at this. I'm looking at a temperature of the water in a kettle over time. So I have 2 units. I have time that's measured in seconds. I have degrees Celsius for my temperature. Time is going to be my independent variable. So I'm putting it on my x-axis. I have temperature, which is going to be my dependent variable that's measured in degrees Celsius. What's happening here? It's the temperature of water in a kettle over time. Now, I know I'm starting at 20 degrees Celsius. Great. I would like to make sure that I'm at 20 degrees. My kettle is rising 4 degrees every 30 seconds. So whatever scale I choose, I want to make sure it's going to be easy for me to show an increase of 4. So I might go up by, probably not going to go up by 1s because I'll run out of room really fast. I could go up by 2s, then my graph is going to start up halfway, which is fine. I'm okay with that. I might go up by 4s. That can work too, but then my graph might not go all the way to the top. Doesn't quite super matter as long as the scale you choose is clear for how you're going to make those jumps. Because I'm making a jump or a rise of 4 degrees Celsius. Do not choose a scale of 5. Okay. I'm going to choose a scale of 2. Why not? So I've got 0, 2, and I'm only going to label every second one. I did not mean to put that in. There we go. 12, 16, 20. Just because otherwise I feel like it would be a little bit too crowded for me. If you feel like you can fit it and it makes sense to you, follow your heart. Okay. And then I'm going to go along the x-axis. Also, keep in mind, if you did not choose a scale of 2 for every box, that is okay. I am totally fine with it. I'm pretty sure on my answer key, I did not choose a scale of 2. So there's that. Okay, for time, it's every 30 seconds. So like, yes, my y-axis is going to be a 0, but I'm definitely not going to go up by 1s. I'm probably going to go up by 30s. So here's 30, 60, 90, 120, 150. Because again, I want to choose a scale that's going to make my life easier. So here it is. Then I'm going to plot some points. So I know I start at time of 0 seconds at 20 degrees. I'm starting at room temperature, I'm imagining. And then every 30 seconds, the kettle temperature rises 4 degrees. So here it is. And I've plotted my points. I'm going to connect my dots with a straight line here. And then I'm going to include an arrow to the right. Things to point out. I'm not including an arrow. I feel like that's just okay there. I'm not including an arrow to my left because it wouldn't make sense for the kettle to be colder ahead of this, because water in a kettle tends to start off at room temperature. Doesn't start off typically super, super cold. Like and I'm assuming that if it's only giving me quadrant 1 of my graph to start off with, it wouldn't make sense for me to have that arrow backwards. I did put an arrow to my right, but I wouldn't do it in all situations. So I put an arrow to my right here because the graph that I'm showing only shows it up to 40 degrees. And I know that if I'm putting water in a kettle, typically I'm doing so that the water boils. Like, unless I have a fancy schmancy kettle that like can give me a whatever temperature I want as the final output. Typically, we want to put water in a kettle so that it boils. Water boils at 100 degrees, so it could definitely go above 40. If I chose a scale and was able to show more of this graph, or I had a follow-up question about my graph and said, what is the domain of this graph? Or what is the range of this graph, given the specific context? I wouldn't say that the range starts at 20 and it goes up forever. Because once water reaches 100 degrees Celsius, it starts to boil. It becomes vapor. So I'm not going to have water at 300 degrees one day. I'm maybe going to have vapor at 300 degrees, I suppose, but not water. Okay? So I'm drawing an arrow here because my graph would continue in that direction. However, if I was ever asked follow-up questions, please note that I do have to consider what is logically possible or feasible, okay? So depending on what scale you chose, if your graph can continue to the right, pop an arrow in there. If you've already reached 100 degrees, do not put an arrow in there, because you should stop the graph when it reaches 100, okay? That is it. That is all. There is some practice that follows, and I hope you have a good time completing that practice. Have a lovely day. Bye.